Okay, so continuing with our finite difference time domain 2D formulation is what we are looking at. What we have seen so far is how to deal with space, right? Spatial derivatives are replaced by finite differences in space across this stencil. Okay. So if you look at your equations 1, 2 and 3, we have dealt with the right hand sides, right? The next thing that is left is left hand sides. Okay. So let's come to that next. Before we move to time stepping, I thought just for sake of completeness, I will also show you the stencil for TM polarization. So far we spoke about TE polarization. So for the TM polarization, right, what were the variables in TM? Hx, Hy, Ez. These are the three variables that I have to think about, right? Previously we were doing TE polarization. So we have seen that the logic has been to stagger all of these three variables by how much? Half a grid. They should not all be at the same point in space, they should be staggered. That was one consideration. Second consideration is we would like to have E at the grid lines, where the grid lines are, so that it is easier to enforce boundary conditions. So with these considerations, the sort of very common choice for the TM stencil is as follows. Right, so you can have your, as before, this can be your Hy. Okay. So Hx is at the center over here, and where should you put Ez? We could put it at the middle of the cell, but then the problem is boundary conditions enforcing. So at the corner of the grid, if I put it, let us say here, it is still half a grid away from the other variables, and it's helpful in satisfying boundary conditions. I could put it also in the middle of the cell, there is no problem. Okay, it's all, it will be consistent. Okay, so this is the TM stencil that we will refer to when needed. Now let's go back to the time stepping part, right? So in time stepping, as always, what we will do is replace this time derivative by finite differences. What was the notation that we had for time? We put it as a superscript, right? So it was written as E superscript n, right? So this was our time index. Okay. Now we said that in space the variables were staggered by half a grid, right? Staggered by what about in time? What should we do? Do the same thing. See, we in these methods we are discretizing space and time. So just as there is a delta x, delta y in the stencil, there is also going to be a delta t, right? So that delta t, the question can be, should I have the variables being updated at the same delta t or some staggering over there as well? So we will see that the same logic, there is nothing special, there is no special preference to space over time. So whatever we do for space is what we will do for time. So we will also stagger them by half a grid. Here it meant delta x, delta y. Here it means delta t. Okay. So let's write it out. So let's take both our Maxwell's equations, okay, and try to write out what happens, right? So very quick, curl of H, forget the current term, right? This is what? D by dt, and the other equation is dB by dt. This is equal to minus curl of E. These are the two equations we have to keep in mind. Okay. So let's see. Let's take the first equation. Okay. So this is our first equation. This is our second equation. So dd by dt, we'll make the same assumptions about the medium, linear, homogeneous, all of that. So this becomes epsilon, right? here is where I have to write down an approximation for dE by dt. Right hand side is going to be the derivative for the curl of h, I mean not derivative but curl of h. Fine. Now, supposing I choose to evaluate, okay, look at for example, in this TM stencil hx is evaluated at one point in space. What is the next point in space? Is it delta x later or is it delta x by 2 later? For hx, where will the next evaluation of hx be? Delta x, right? So, when I look at, for example, the electric field derivative over here, the adjacent points for E should be delta t apart or delta t by 2 apart? Delta t apart, same logic I am applying over here. Okay. So, let us say E is evaluated at integer points, integer time grids. Okay. So, en plus 1, en plus 2 and so on. So, what should I write over here in this square bracket over here for time derivative? Very simply, it should be
en plus 1 ij.
So, or I can just write en minus
en minus 1
divided by delta t, right. So, I am just writing right now in vector form, okay, right. And if I have done this for the electric field, then the magnetic field should have been evaluated at what time? Should it be n? So, I am asking what I should write over here as the exponent, not exponent, superscript. Should it be n minus 1 or something else? N minus half a grid point, right. So, this should be n minus half. Right, because again, what was the logic over here? When I looked at the Taylor series and I found out f of z naught minus h, so plus h, and minus f of z naught minus h divided by 2h. This is a very good approximation of f prime at which point? Z naught, which is the average of this guy and this guy. Similarly, here on the left hand side I have E at n and E at n minus 1. So, what is it a very good approximation of? Of something at n minus half. That is why I have written this as n minus half. Okay. What will now the rest is easy. What will the second equation imply? So, B is mu naught h in vacuum. So, this will become mu naught. Now, let us write this carefully. So, maybe we will write the right hand side first. Curl of E. Where am I evaluating the electric field? What is the superscript for electric field I should write here? Integer points, that is the convention. The simplest integer point is n, right. So, now it follows, what should I write over here? So, h minus h divided by delta t. Okay. So, h n plus half n minus half, right. So, once again I am using the idea here, average of z naught plus h and okay. So, now let us just rewrite equation 1 over here. Okay. So, in terms of all the time indices, which is the future most time index over here in equation 1? N, right. E n is the farthest I can go in time in this equation. So, if I want to write this over here E n, I can write this in terms of E n minus 1, right, and a plus delta t by epsilon, what else? Curl of h evaluated at n minus half. Yeah. Similarly, what is the farthest in time in this equation? N plus half, right? So, h of n plus half is equal to h of n minus half minus mu naught, sorry, delta t by mu naught curl of E at n. Well, okay, so let me start by saying that here, this line over here, when we say that E is evaluated at integer time grids is a choice. I could have said E is evaluated at half integer time grids. Okay. Once I fix where E is evaluated, H automatically becomes staggered by half a grid, right. So, I have got E evaluated at integer time instance, and now if I want the value of E at a half time integer, then what should I do? Like earlier, take the average. If you want it at some other point, interpolate. Okay. So, the choice is up to you, but once you fix one, everything else gets fixed. Question? Yeah, that's what I said. It's my choice. It's not coming from physics or math. It's a choice. It's a convention. Once I fix it, but then I have to be consistent with the rest. So, I could have said h n, then I am forced to do E n minus half n plus half. Okay. Finally, remember that the discretizations are going to be so fine that it really will not matter. So, now let us move our attention to these two equations that I have written over here. Okay. So, one of the sort of basic principles in FDTD is that once I get the once I make this grid, I am going to evolve the field in space and time. So, it's space stepping and time stepping. Based on previous values of field, I will get future values, and so also for space. Okay. So, if I were to make a timeline, okay, so now let us make a time axis. So, this is maybe I should make it dotted. Time, okay. Time is what I am looking at, and let us say one point over here is E n minus 1. Okay. So, if E n minus 1, then let me draw one more point over here. This will be E n. Okay. This is as time is progressing. Similarly, in where should I draw the magnetic field values? In between these, right, because it is half a grid. So, for example, this I will draw with a cross. This will be h n minus half, and then this guy will be h n plus half. Okay. Now, let us look at these two equations. Okay. So, this is equation 3 and equation 4. So, what is equation 3 telling me? Let us pay very close attention to this. Supposing I know everything in the past, okay, and I want to evaluate the current value of electric field. So, past means the right hand side of this equation. That means I know E n minus 1, I know h n minus half. Okay. So, to evaluate E n, what all do I need? E n minus 1, h n minus half, right. So, I can draw it like this, that this value goes into here and so does this value. Okay, let us draw it actually down like this. Right. Now, let us then go to equation 4. Okay. Equation 4 is telling me what? Equation 4 is talking about h n plus half, right. So, you can think of this as this equal to sign is sort of dividing the present from the past. So, the right hand side requires what? Electric field at n, magnetic field at n minus half, right. So, if I were to draw arrows over here, what should I show you? For example, this guy. goes in here, and this guy goes in over here. So, I am just graphically interpreting these two equations, that there is a half grid and one grid away. These both are required to evaluate the field at a given time instant. So, for example, En, it is not enough for me to just know electric field at the past, I also need to know magnetic field at half grid past. Okay. So, the way this diagram has been drawn, it looks like a frog that is leaping in some sense, right. So, that is why this scheme is called a leapfrog integration scheme. Okay. Leapfrog integration. Okay. So, this is a very characteristic thing of your what you call finite difference time domain method, where there is this half a grid is really what is bringing everything out. Okay. Now, we have seen in 2D it is possible to visualize space and time. Okay. So, right now for example, the stencils which I have shown you, we are looking at the top view, but now if I also wanted to visualize the time axis, what can I do? I can move it on the z axis, right. So, one common way of understanding things over here is you put time on the z axis, you call this, let us say, y, and you call this x, right. This is your E cell at some time instant, right. This can be your delta t, can be this, right. So, that is how it goes, and so on. So, what is the FDTD scheme all about? It is using these update equations to time step the fields and space step the fields. Okay.